Okay, so let's discuss this question quickly, how to make a PCR mix. So we're going to use the example question from 2023, test 1, and the question reads, you have 5 samples that you'd like to test for the presence of the SARS-CoV-2. I don't know if it's the correct way to say it, but yeah, SARS-CoV-2, that's a gene. And each sample should be run in a total volume of 10 microliters. Using your own figures, show how you would design the master mix for the 5 samples. So to prepare a PCR master mix, you need certain components that we're going to list out, and then those components need to have a volume per reaction, so a volume per sample, that's what we're talking about here, and then volume for the it's not supposed to be pair 4, so volume for the 5 reactions, the total volume, that's the master mix that we're talking about. So how to prepare that? Firstly, get your components. So these components, we're going to list them out in no particular order, but let's just put them here. We're going to need the buffer, and then secondly you're going to need the dinucleotide phosphate bases. These are the nucleotides, and then you're going to need your forward and reverse primers. Okay, so you need those, and then number 5, you're going to need your magnesium ions, and then magnesium ions are going to come from magnesium chloride, MgCO2. And then number 6, you're going to need your DNA Taq polymerase. Taq DNA polymerase. This is the enzyme that we use in the PCR. And then number 7, you're going to need the DNA template, of course, that you're going to add at the end of the whole thing. And then number 8, you're going to need the PCR grade water. Okay, let me just write that. The PCR grade water. Alright, so those components, you have them like that. But then the question says using your own figures. So this is where now the trick comes in. You need to find the volumes that you're going to use per reaction. So you cannot just use any volumes, but rather you need to use a certain formula that will help you come up with the volumes per reactions. Of course, you're using our own figures, but you can't just put your own figures in here. So the formula, the volume that we are trying to find here, be determined by the desired concentration multiplied by the total final volume, however you might choose to put it, and then divide all of that by the stock concentrations. Okay, so where do you get all these figures? The desired concentrations are the own figures that we are going to be talking about. So you put you basically decide what concentration you need to have in the final volume. So once you put that figure there, is the one that is going to help you find the volume per reaction. Then stock concentrations, these ones are given. There are certain stock concentrations that you have to take note of for these components that are here. Okay, so I'm going to give you these and you're going to have to memorize them. So firstly, for the buffer, so the good thing is that all of these all the way up to down here, okay, these are the only ones that are different. The last 3 are different, but the first 4 will all be 10, 10, 10. So the buffer will be 10x, the nucleotide millimolar in concentration. So these are concentrations, stock concentrations that you need to dilute into a certain volume and the like. So this formula helps you find the final volume that you're going to use of each component per reaction. Okay, this one as well. But the magnesium chloride comes in 25 millimolar concentration. The Taq polymerase comes in 5 units. So 5U per microliter, yeah. And then the template DNA, you can use anywhere from 1 to 5 microliters depending on the size that you need, or the size of the, or volume rather, that you need at the end of the day. So now that you have these stock solutions, these are the figures that you're going to have to memorize. So the different ones here, 5, 25, and 1 to 5. The rest are just 10. So once you have that down, you can now get to the formula here. So desired concentrations is what we need. Stock solutions we already have. And then the total volume is the 10 that you've been given in the question here. It's the total volume. So desired concentration, if you want, you can actually make separate column there with the desired concentrations. So with the desired concentrations, you can just choose within the normal ranges. So for the buffer, for example, we can pick, we say our buffer for 10 maybe just 1x as the concentration. Usually that's within the normal range. I'll put a picture in the thumbnail that has more like the reference values that you can use to put, because here we are using our own figures, so just put figures that are close to the figures that are the normal ones for reference, the ones that we use in conventional PCR. All right, so there we're going to have for the dinucleotides we can use let's use a 0.5. Forward and reverse also, let's use a 0.5 for each. And then for the magnesium chloride, let's use 0.8. Let's just use a 0.8. And then for the TAC polymerase, let's use a 0.02. Okay. And for the template DNA, okay, let's just use a 0.2 here instead of a 0.02. And then let's use a point for the DNA template. Okay, let's use a 0.4. Yeah, I'm just coming up with these figures, and then yeah, we'll see how they come together. For the PCR grade water, you're going to find that after finding the volume reaction of all of this, then you subtract that from the total, you see how much water you're supposed to add, then that's when you find your answer there. So let's do that real quickly. Plug in these figures into the formula and then find what we need. So for the first one, it's a straight one. Desired concentration is 1. Multiply that by 10. Multiply that by 10. Divide by stock concentration is 10 again. So that will give you 1. So that is 1 microliter for the buffer. And then for the dinucleotides, again doing the same thing, 0.5 multiply by 10, divide by 10. So 10 cancels out. That means you're going to get a 0.5 microliter here as well. So if you check all of these that have 10, because the 10 is our denominator, you find that all of these will just be the same thing that we had as the desired concentration. So it will be 0.5 there, microliter, 0.5 microliter there as well. The only different one that we're going to have here, the last 3, which will be 0.8 multiplied by 10 divided by 25. So let me just pull up my calculator real quick and then sort that out. So 0.8 by 10 divided by 25, that gives me 0.032 microliters. And then for the TAC polymerase, we have 0.2 multiplied by 10 divided by 5. The 5, this one is 5, and the 25 is the one that is here. So that's where I'm getting the figures. So that would be 0.4 microliters for the TAC polymerase, and then for the template. The template is 0.4 multiplied by 10 and divide that by oh sorry, for the just a quick one, for the template you just choose you can just choose, because here we're working with depending on the size of the DNA template. So this one usually you can just choose to put, yeah, just put a certain amount, and usually it's anywhere from 1 to 5 microliters. So that's what I would advise. Instead of doing the calculation for this one, just do the choose 1. So just put 1 microliter for that. Yeah, that is what I would advise. But if you want, you can do the same calculation even here. It works. It also works. But let's just use that for now. And so now there's a total that we need to have down here. So the total is supposed to be 10. So for us to find for the water, we need to subtract the total of this from the 10, then we get the amount of water we're supposed to add to that PCR mix. So let's put 1 plus 0.5 plus 0.5 plus another 0.5 plus 0.32 plus 0.4 plus 1, so that gives us 4.22. Subtract that from 10, that means our water, the amount of water we need to add, 4.78 microliters of water. So now we have volumes per reaction. So volumes per reactions have been solved. We need to find the volumes per 5 of the master mix of 5 reactions rather. So we're going to multiply across the board by 5 basically. So multiply 1 by 5, basically that would be 5. This one will be 2.5. I'm just multiplying by 5, that will be 2.5, another 2.5 here. These are all microliters. You can add that, you should add that. So 0.32 multiplied by 5, that's 1.6, then 0.4 multiplied by 5, that gives you 2, and then another 5 here, and then 5.78, multiply that by 5, that gives you 28.9. So if you had to add all of these, plus 5 plus 2 plus 1.6 plus 2.5 plus 2.5 plus another 2.5 plus 5 should give you 50, because when you multiply the total by 5 it will give you 50. So these will all give you the total if it were multiplied by 5. So that means the master mix for 5 will have 5 milliliters, but this is not the 5 milliliters we're going to make. In the actual making, what we're going to have to do is to add 1 extra sample volume. So we're going to multiply it by 6 instead and make a master mix of 60 microliters. Why we need to make that? So that in case of any errors that we encounter during pipetting, or maybe the spillages, there is those slight errors that you have to account for during the processes that are involved in this PCR master mix formation. We're going to have to account for them so that you don't run out of reagent basically. So we're going to make one more than, so this is a hard rule. As you are making a PCR master mix, if you have 5 samples you need to test, make a PCR mix for 6. Okay, if you are having 10, make for 11. You get the idea. So that is basically that. So as you are explaining what you just did in this table, this is step 1. Then step 2, you just start explaining what you were doing here, and then in the last statement you say the final volume of the PCR mix will have to be 1 more than the number of samples that we are having, so that for the reasons that I just mentioned. Then other than that, you'll be done. That will be, so just explain what you are doing here, and then lastly include why you are making 60 microliters instead of 50. Then you'll be done with your PCR mix making. All right.